Okay, so when we talk about being soluble within a solvent, we typically mean that that substance will dissolve. Salt, for example, table salt will dissolve in water, and so we'll say that sodium chloride is soluble in water. But the reality is it'll only dissolve up to a certain point. If you have a cup of water and you start scooping table salt in it, it will dissolve the first scoop and perhaps the second scoop, but before long it will stop dissolving. And so we know that even something soluble like table salt, there's a limit to how much the solvent is going to be able to solvate, to form a solution. And so we call that the solubility. And the solubility, we can talk in terms of how many moles of solute for every liter of solution that we can form. So the moles of solute for every liter of solution, or sometimes we'll talk about in terms of grams of solute for every liter of solution. And we can get really quantitative with this and solve lots of really interesting quantitative questions. But for this class, we're just going to talk about sort of basic trends, whether something has a higher or lower solubility under different conditions and things. And so you don't need to worry too much about the mathematical differences between these two. They both indicate how much solute you can dissolve in a given volume of solution. And there's a couple of terms that we can use to talk about the ratios that the solute and the solvent can take. So the first one is miscibility. So two liquids are said to be miscible if they can combine in any ratio. So if I had a cup of water and I decided to start putting spoonfuls of ethanol into that water, I would find that they would mix no matter how much ethanol I put. So ethanol has sort of an infinite solubility in water. And likewise, water has an infinite solubility in ethanol. I can mix them however I like. And so those are two substances which are miscible with each other. And then for solvent-solute pairs that are not miscible, then you can generate a saturated solution, and that means it's a solution that has that maximum amount of solute that it can have, that it won't take any more solute. You can tell if a solution is saturated if you add more of the solute and it doesn't dissolve. So if I have a glass of water and I put a scoop of salt in there and it all dissolved, then I know that it hasn't yet been saturated. If I add a second scoop and it mostly dissolves, but there's a little bit of salt crystal that remains on the bottom of the glass, and if I stir it and I wait a sufficiently long time that I know it's never going to dissolve, then that tells me that I have a saturated solution. Really, if there isn't some solid present, then you don't really know that it's saturated. It might be close to saturated, if you happen to add just the right amount so that it will dissolve all of your salt, but not be able to dissolve anymore. Well, then you will have made a very precise measurement. But it's easiest to just dump in a little extra, and then you can be sure it's taken absolutely as much as it can, and it won't be able to take any more. Now, actually, I want to talk about the next one in a minute. Okay, sorry. So the solubility can depend on different conditions. And so the first thing we want to look at is temperature. As I change the temperature of a solution, then the solubility will change as well. So here we have, shoot, which figure is this? This is figure 9.3. This is a figure in your textbook that shows solubility curves in water for lots of different substances. So you can see on the y-axis, there's the solubility in grams per liter. And some substances you can dissolve a fair amount. You know, at room temperature, it looks like sodium nitrate. You can dissolve 80 or 90 grams of sodium nitrate for every, that's for every 100 milliliters of solution. And so, you know, that's, so that's going to be almost like more sodium nitrate than water. It holds an awful lot. Others are lower, but the x-axis shows the temperature, and the temperature changes based on the temperature, and it goes in different ways. So let me pick one like that sodium nitrate. So if I have NaNO3 solid, and the process of solvation for NaNO3 solid is to go to Na plus aqueous plus NO3 minus aqueous. Right? That is the chemical equation for the solvation of sodium nitrate. And you'll notice that as the temperature increases, then the solubility increases, or in other words, there's more sodium ions and nitrate ions that are allowed to be in solution. Well, solvation reactions are equilibrium reactions, and so we can explain this trend in terms of Le Chatelier's principle. If I increase the temperature and the reaction shifts more toward products, then what does that tell us about the enthalpy of reaction? That tells us that it is endothermic, and we can put heat on that side right there. If you see the potassium bromide, glucose, which is sugar, sodium acetate, potassium bromide, copper sulfate, those all have an endothermic enthalpy of solvation. So increasing the temperature increases their solubility. You can notice on that chart there are a couple others that seem to go the other way. Sodium chloride is one of them, and cerium sulfate is the other. So let's look at that cerium sulfate. So Ce2 SO4 solid is in equilibrium with 2Ce3 plus aqueous plus 3 SO4 minus aqueous. Cerium sulfate. And as we increase the temperature, then the solubility goes down. That means if I increase the temperature, the reaction is shifting away from products back over toward reactants. And so that tells me that heat belongs on this side as if it is a product. And so it is an exothermic process to dissolve cerium sulfate. Like sodium hydroxide I mentioned earlier, that can boil water if you add enough of the solid sodium hydroxide salt to water. Sodium chloride appears to be in that camp as well. And so that is all of our solid solutes. It could go either way. This other graph over here on this side is showing the same thing, the solubility of different solutes in water. But this time we're looking at gases. You'll notice, what do we have here? Carbon dioxide, xenon, oxygen, and nitrogen. And first of all, their solubilities are all very low. We're looking at millimoles per liter. Their solubilities of gases in water are all very low. But you'll notice that all of them are going to decrease their solubility at higher temperatures. So cold water can hold more oxygen than warm water, which is why Arctic seas actually support more life, more fish, at least by mass, than tropical waters. There's more oxygen dissolved in cold water, and so it's a little bit more amenable to life than warm water in that respect. So all gases will behave this way. And so if it's a gas, you already know that it is going to be an, what is it? It's an exothermic, no. Increasing the temperature decreases the salt. Yeah, it would be an exothermic enthalpy of solvation, and increasing the temperature decreases the solubility. Now, the fact that we can change the solubility, oh, sorry, there's one more law. There we go. Okay, so gases have a certain solubility in water according to a formula, and we don't need to get into the math again. We're talking mostly in terms of trends here. But gases follow what we call Henry's law, that says that the solubility is proportional to the gas pressure above the water. And so we can explain this because when you have a gas solute in solution, it's always going to have some gas particles that will pop back up into the vapor phase, and then some gas particles from the vapor phase popping back down into the aqueous phase. So there will always be an equilibrium where you have both the gas and the aqueous. Let me write that equation up here real quick. So for example, you can have CO2 gas in equilibrium with CO2 aqueous, okay? And if I increase the pressure of the carbon dioxide gas, then that means there's going to be more carbon dioxide gas particles, or at least they'll be, they will be more dense, the gas particles in the gas phase, and they will collide with the water surface more frequently, and so they will stick to the water and get dissolved at a more rapid rate than they do at low pressures. And that's going to shift the equilibrium so that you have a higher concentration of carbon dioxide gas in solution. This can also pretty easily be explained by Le Chatelier's principle. If I increase the pressure of carbon dioxide gas, then that will shift the reaction toward products. Here in this case, the dissolved carbon dioxide will increase as well. This is why carbonated beverages, for example, they're always in a pressurized can. The way you get carbon dioxide into the water is by, in the factory, pressurizing those cans with carbon dioxide in particular. The headspace in that can has carbon dioxide, I forget it, it's at several atmospheres, maybe 2 or 3 atmospheres of pressure. And that's what gets the carbon dioxide into the solution. And now, I talked about miscibility and saturation, so now we can talk about supersaturation. So a supersaturated solution is one where you actually have more solute in solution than you should be allowed to have. The way you accomplish this is by setting up conditions where you have a high solubility, you dissolve a bunch of your solute, and then you revert back to conditions with a lower solubility. So as long as we're talking about carbon dioxide and soft drinks, then your soft drink is actually a supersaturated solution of carbon dioxide. As soon as you open that can, it's no longer going to be pressurized. That's why you hear the hiss as it opens. And when the carbon dioxide pressure drops down low, in fact it drops to close to 0, as it's replaced with regular air, then the solubility of carbon dioxide drops precipitously. And all of that carbon dioxide that was dissolved in solution is now going to be coming out of solution. That's what makes carbonated drinks fizz. That's what generates the bubbles, is that water is super saturated. It cannot hold all of that carbon dioxide anymore, and so it's going to release the carbon dioxide in the form of bubbles. Now if we go back a couple of pages here to the solubility of different solids in water, the temperature dependence can come into play as well. If you heat up a solution of, say, glucose, you see it's got a rather sharp curve there. At higher temperatures, glucose solubility is very high. You can dissolve a whole lot of sugar in boiling water and then cool it down, and it will be a supersaturated solution. What's really fun is sometimes these supersaturated solutions are metastable, meaning that they can kind of remain in that state for a long time until they're disturbed. And so in the case of a supersaturated glucose solution, you can cool it back down to room temperature. If you do that carefully, then it's a metastable condition, and it will just look like a regular old glass of water until you drop a seed crystal, and that will begin the process of precipitating out all of that excess sugar. And I did a demo earlier in the year of a sodium acetate supersaturated solution where we dropped a seed crystal and it crystallized to form a solid. And it looked sort of like this. This is their picture of a acetate solution that has been supersaturated and then crystallized. So let me turn that figure off. Okay, so the point is that solubility, the measure of how much solute you can dissolve into a solvent, can change. For gases, you can easily change the gas pressure. Higher pressures is a higher solubility. And for other things, you can change the temperature. For some solid solutes, like sugar, like sodium nitrate, then the higher temperatures will lead to higher solubilities. For some solids, like sodium hydroxide or sodium chloride or cesium sulfate, then actually the lower temperatures will have the higher solubility. But in any case, you can change the temperature whichever way you need to raise the solubility, dissolve a higher amount of that solute, and then revert to your original temperature, and you have a supersaturated solution.